In this video, we'll be discussing about location of roots slash position of roots. Let's consider a polynomial function axk plus bx plus c where a is not equal to 0 and abc belongs to R. It is a quadratic polynomial because of degree 2. Now, if we consider the equation for this axk plus bx plus c equal to 0, let's consider the roots as alpha comma beta where alpha is less than beta. Now, what we will be discussing in this topic is, let's say for example I have a equation xk minus 5x plus 6 is equal to 0. Okay, so I already know the graph of this polynomial will be like this and the roots will be 2 comma 3. In this case, because I know the roots of the equation, I already know where 5 by 2 will come, where 4 will come. Okay, on this graph where the 4 will come ahead of both the roots, so I will be writing it as 2 is less than 3 less than 4. The number 4 is ahead of the roots. If I say 1 is less than both the roots. Okay, so in this case, because we know the roots, we already know the location of the any number which I will be putting on the number line. If I'll consider the equation as like this, xk minus px plus 6 is equal to 0, and I say that both the roots of this equations are more than 1, find the value of p, then this will be a problem. This will be a good problem because I don't know the exact roots and I just know the condition that both the roots are more than 1. So the diagram for this particular problem will be like this, that both the roots are more than 1. Or let's say if I consider the roots as alpha beta, and I'll be doing some calculations to find the value of p. So in this particular topic, we'll be doing these kind of problems. Some variable might be introduced in an equation and he will say that both the roots are less than 1, both the roots are greater than 1, say one root is behind 1 and one root is ahead of 1. These kind of statements will be there and you have to find the value of the variable. Thus, we have divided the location of roots into 6 subtopics which cover all the kind of problems. Now, let's look at them one by one. Now, let's look at the case 1 in which the number k is between the roots. Okay, so if the number k is between the roots, the parabola can be drawn in two ways like this. Because k is between the roots, in this case, the parabola is upward and k is between alpha and beta. We have already considered that alpha is less than beta. In this case, the parabola is downward and k is again between the roots. Now we have to find the condition which is applicable for every quadratic polynomial which is there. Okay, so that's why I have drawn the two parabolas. Now parabola cannot be like this. If parabola will be like this, like above x-axis, then k cannot be between the roots because there are no real roots. In this case, there is no real roots. So definitely there are two kind of diagrams which are possible. One is this one and the other is this one. So for that, if I consider, now I have to make the conditions which will be applicable for all the parabolas in which there is a possibility that k lies between both the roots. Okay, so in this case, if you see a is greater than 0 and a is less than 0 in this case, because this is upward parabola, a is greater than 0. In this case, because it is a downward parabola, a is less than 0. Okay, so obviously on a we cannot make a condition. If you see this coordinate, the vertex, not the vertex coordinate, the coordinate which lies on the vertical line x is equal to k, this coordinate is k comma f of k. Because we don't know the location of the roots, we don't know whether k is positive or k is negative. But in this particular case, definitely f of k will be negative because f of k is the y coordinate which is below x-axis. And in this case, if you see this coordinate, it will be k comma f of k again. And in this case, f of k is greater than 0. It is positive because it is above x-axis. Now, if you see a is positive, f of k is negative in the upward parabola, a is negative, f of k is positive in the downward parabola. If we multiply these two, we will get a into f of k which is less than 0. So what this shows us, that a into f of k will be negative in both the case. So definitely we got a condition that a into f of k is less than 0. Now the second condition which is but obvious is that d should be greater than 0. Okay, so d should be greater than 0 is also a condition because both the roots, because here the alpha and beta, both the roots are real and distinct. That's why d should be greater than 0. But once you solve the problems, you will get to know that if I take the intersection of both these cases, because I want this should also hold, the first condition should also hold, and the second condition should also hold. The first condition will hold only in the case if d is greater than 0. So the final necessary and sufficient condition for this particular case is a into f of k is less than 0. Okay, I'll just repeat it once again, that we wanted to find out the condition that a number k lie between the root alpha and beta. Okay, so I have drawn two particular cases in which k can be between the roots. One is upward parabola and one is a downward parabola. In upward parabola, we found out that a is greater than 0 and f of k is negative. In this case, a is less than 0 and f of k is positive. So product of these two terms will be giving the same sign. So what we did is we wrote the condition a into f of k is less than 0, which appears to be a sufficient condition, or say necessary condition right now. When I checked d is greater than 0, so that is also true for both the cases because both the roots are real and distinct. So now if I take the intersection of both the cases, we will definitely get a into f of k is less than 0, because a into f of k will be less than 0 only if d is greater than 0. Just hear this again. A into f of k will be less than 0 only if d is greater than 0. I'll just draw some more diagram which will prove this fact. Now let's see these three diagrams. In the first diagram, we have there are no real roots. In this case, there is no real roots. Obviously, this is not the possible case for us, but still if we see, in this case a is positive and let's say k is here at this point, then f of k is also positive, then a into f of k will be greater than 0 because both a and f of k is positive. In the second case, because the parabola is downward and below x-axis, f of k will be negative and a will be negative. In this case also, if you multiply a into f of k, it will be positive. In the third case, k is outside the roots. Now f of k is positive in this case and a is also positive in this case. So product of these two terms will also give me a into f of k is greater than 0. So if you clearly see that a into f of k will be negative only in these two cases when k is between the roots, and hence automatically d is greater than 0 will be make sure. So a into f of k will be less than 0 is the necessary and sufficient condition for this particular case. So you need to remember now one thing, that case 1 was if k is a number which lies between alpha and beta, and the necessary and sufficient condition for this particular case is a into f of k is less than 0. Okay. Now moving on to the next case. In this, alpha is less than k1, less than k2, less than beta. It means there are two numbers k1 and k2 which lie between both the roots. So I have again drawn two particular cases which are possible. One is a upward parabola in which alpha is less than beta and k1 k2 lie between these two roots. This is upward parabola. This is downward parabola in which alpha is less than beta and k1 k2 lies between alpha and beta. Okay, now this is a extension of the case 1 only, so we can directly write in this particular case that here f of k1 is negative, f of k2 is also negative, because it is already given in the problem that k1 is less than k2. So I can directly write a into f of k1 should be less than 0. What this condition will make sure, it will make sure that k1 is between the roots alpha and beta, and also a into f of k2 is less than 0. What will this make sure? That k2 is between the roots, and we need not to check that k1 is less than k2 because it is already given in the problem. In this case also, if you see, f of k1 is positive because it is a y coordinate at the point x is equal to k1, and f of k2 is also positive. So a is negative, a into f of k1 will be, a into f of k1 will be negative. Also a into f of k2 will be negative. So combining both these cases, you can easily see that the condition for this particular case is a into f of k1 is less than 0 and a into f of k2 is less than 0. Now if you got to know some facts in these two cases, first condition in most of the cases will be dependent on a and f of k. Okay, so from next time onwards, if we see the next case, we need not to draw both the parabola. You need not to draw both the parabolas. You can easily draw one parabola and try to conclude the conditions from them. Remember that the first condition will be on a into f of k only. Okay, in this case, k is less than alpha less than equal to beta. So there are I have drawn only upward parabolas only in this case, because we already know that the first condition will be dependent on a into f of k. There are two possible cases. One is that k is less than alpha less than beta, and the other is that k is less than alpha equal to beta, and we combined them both to get this condition that k is less than alpha less than equal to beta. Now the first condition is based on a into f of k. Now in this case, a is greater than 0 and f of k is also greater than 0. So product of these two will be a into f of k is greater than 0. So the first condition definitely will be a into f of k is greater than 0. This holds for this case also. A is greater than 0, f of k is greater than 0. So product will be a into f of k, which is greater than 0. Now the second condition in this case will be d is greater than 0 or equal to 0, because if you see the first diagram here, d is greater than 0, and in the second diagram d is equal to 0. So combining these two, you will get d is greater than equal to 0. It is very important to apply this condition here, because a into f of k greater than 0 doesn't make sure that this condition doesn't make sure that d is greater than 0. Okay, it doesn't make sure that d is greater than 0, but in the previous cases, a into f of k less than 0 was already making it sure that d is greater than 0. Okay, now the third condition is that k is less than minus b by 2a. What the third condition will make sure is that the k lies on the left hand side of the vertex. So if this is the vertex, the x coordinate of the vertex is minus b by 2a. Okay, you might be knowing the x coordinate is minus b by 2a and the y coordinate is minus d by 4a. Okay, so the x coordinate is minus b by 2a and the y coordinate is minus d by 4a. So k is less than the x coordinate of the vertex. Here also the x coordinate of the vertex will be minus b by 2a comma 0, because d is 0 here in this case. So k is less than minus b by 2a. So for this particular condition, what are if k is less than alpha less than equal to beta, what are the three conditions? The first condition is a into f of k is greater than 0. Second condition is d is greater than equal to 0, and third condition is k is less than minus b by 2a. Okay. Now moving on to the next case. In this case, alpha is less than equal to beta less than k. It means k is more than both the roots. Both the roots can be distinct as well as equal. So this is similar to the above case only. In the difference only is that k is more than both the roots. So the first condition will definitely be a into f of k is greater than 0, because k is outside the roots. You can easily check a is greater than 0 here. F of k is also positive, so the product of these two terms will be positive. In this case also, a is greater than 0, f of k is greater than 0, product of these two terms will be positive. Because this does not make sure about the real roots, so you need to apply the condition d is greater than equal to 0. Why d greater than equal to 0? Because roots can be equal as well as distinct. Third condition. Now if you see clearly in this case, if you does not apply the third condition, the case 3 and case 4 will both have same conditions. Let's check it. The first condition is a into f of k is greater than 0. The second condition is d greater than equal to 0. This is also same in this particular case. That's why we have to apply the third condition, which is necessary and sufficient. So k is greater than minus b by 2a. Okay, so the three condition for this particular case is that a into f of k is greater than 0, intersection d is greater than equal to 0, intersection k is greater than minus b by 2a. Now you might be getting to know one more thing which is very clear, that if a into f of k is greater than 0, then k cannot lie between the roots. K will be either outside the roots, or otherwise there will not be any real roots for the particular parabola. In this particular case, k1 is less than alpha, less than equal to beta, less than k2. Okay, so the diagram depicting this particular condition is the red one, and the black one need not to be there. I have drawn the black one to specify one particular condition. Okay, here you see k1 is less than alpha in the first diagram, which is further less than equal to beta and less than k2. There will be one more case when both the roots are equal and the parabola will be touching x-axis. Now the first condition which can be seen from the diagram 1 is that a is greater than 0, and here f of k1 is greater than 0. Okay, the condition will be a into f of k1 is greater than 0. This will make sure that k1 is outside the roots. It can be ahead of alpha and beta, it can be behind alpha and beta. So this will make sure that k1 is outside the roots. Second condition, a into f of k2 is greater than 0. What will this make sure? That k2 is outside the roots. You already know that a into f of k greater than 0 does not make sure there are real and distinct roots. We need to see that d is greater than equal to 0. Okay, d is greater than equal to 0. What will this make sure? That there are distinct roots, or it might be equal. Now the fourth, which is necessary and sufficient condition for this particular case, is that if you see these three conditions are also applicable on this particular diagram, the diagram 2. Okay, you see here also f of k1 is positive, a is positive, f of k1 is positive, and f of k2 is also positive. Okay, so if you see that first condition will satisfy this particular case, second will also satisfy, third will also satisfy, but we don't require this particular case, we require the first one. So to distinguish between the red diagram and the black diagram is that you need to apply this condition, k1 is less than minus b by 2a less than k2. This will definitely give us the first particular diagram which was required in our particular case. Okay, so let's once again go through this thing. A into f of k1 greater than 0 will make sure k1 is outside the roots. A into f of k2 greater than 0 will make sure k2 is outside the roots. D is greater than equal to 0 will make sure that roots are distinct and equal. And the fourth case is that k1 less than minus b by 2a less than k2, which will make sure that k1 is behind the roots and k2 is ahead of the roots. You need to take, while solving the problems, you need to take intersection in all these cases. You need to solve the inequalities and take intersections to get the final answers, because all these conditions are required. Now the next case is k1 is less than alpha less than k2. In this particular case, the condition is k1 is less than alpha less than k2. It means one of the roots of the quadratic polynomial lies between k1 and k2. This is also one of the results of intermediate value theorem, which you will be studying in the chapter continuity. Okay, so let's discuss what will happen. Now if you see the diagram 1, it is an upward parabola where alpha lies between k1 and k2, and alpha, because it is upward parabola, f of k1 is positive in this case and f of k2 is negative in this case. Okay, in the second diagram, the parabola is downward, f of k1 is negative in this case and f of k2 is positive in this case. So what will happen, because the graph is continuous? What do you mean by continuous graph? That if you draw the diagram, there is no break in these two values. So if you see that f of x is continuous in k1 to k2, which we can easily state that because quadratic polynomial is a polynomial function. It is a real polynomial function. It will be continuous on x belongs to R. Because f of x is continuous in k1 and k2, and for this particular case, we are getting the condition f of k1 into f of k2 is negative. How we are getting this condition? In the first particular diagram, f of k1 is positive and f of k2 is negative, and the product of these two terms will be negative. In the second diagram, f of k1 is negative, f of k2 is positive. So product of these two terms will be negative. So the necessary and sufficient condition for a root to lie between k1 and k2 is f of k1 into f of k2 is negative. This condition can be generalized on all the functions, and it is used heavily to check that a root lies between any interval or not. Okay, for example, if I have any other function which is might say like this increasing, and I have a number k1 and k2, if I want to check whether the root alpha lies between k1 and k2, then you can easily check that f of k1 is negative and f of k2 is positive in this particular case. So f of k1 into f of k2 will definitely be negative. We can state this as, if a graph goes from negative to positive, say here graph is negative, here graph is positive, and graph is continuous. So if a graph goes from negative to positive, definitely it will be 0 between those two values and it will give the root. Or the graph goes from positive to negative, say in this case the graph is going from positive to negative, so definitely in between these two values there will be a root. So I hope it is clear that for this particular case the condition will be f of k1 into f of k2 is less than 0, and this is also one of the results of intermediate value theorem. Let's briefly revise this lecture. Location of roots. Case 1 was there is a number k which lies between alpha and beta. The condition was a into f of k is less than 0. Okay, and this is necessary and sufficient condition. We need not to check d is greater than 0 or not, because only in a f of k less than 0 the k lies between both the roots. Okay, the next condition was k1 and k2 both lie between alpha and beta, so we made sure that k1 will lie between the roots and k2 will lie between the roots. So a into f of k1 is less than 0 and a into f of k2 is less than 0. The third condition was k is less than alpha less than equal to beta, that k is less than both the roots. So the condition was a into f of k is greater than 0, because k is outside the roots now. D is greater than 0, which will make sure that there are two distinct roots. They might be equal. K is less than minus b by 2a will make sure that k is behind the roots. Similarly, the fourth case, the only change was k is ahead of the roots. So only change in the condition was k is greater than minus b by 2a. In the case 5, k1 and k2 are outside the roots alpha and beta. So first condition will be a into f of k is greater than 0. A into f of k1 is greater than 0. A into f of k2 is greater than 0. This will make sure that k1 and k2 are outside the roots. D greater than equal to 0 will make sure roots are real and distinct. And the fourth condition will make sure that this case, the second diagram which I had drawn with the black should be not considered. We have to consider that k1 should be behind alpha and k2 should be ahead of beta. So k1 should lie between minus b by 2a should lie between k1 and k2. And the sixth case was IVT, which states that if there is a root between k1 and k2, then f of k1 into f of k2 is negative.